now here's the million-dollar question. How do we choose the best K for KNN? If you get this wrong, your model can go from brilliant to completely useless faster than you can say overfitting. But don't worry, I've got you covered. Imagine you're in a new city and want to find the best pizza. If you only ask one person, K1, and they just so happen to love pineapple on pizza, well, you might end up with a questionable recommendation. On the other hand, if you ask 100 people, K100, you might get such a generic response that you miss out on the really good hidden gems. See the problem? Choosing K is all about finding the right balance between bias and variance. If K is too small, e.g. K1, the model becomes too sensitive to noise. One weird data point can throw everything off, just like relying on that one pineapple-loving pizza enthusiast. If K is too large, the model smooths out too much and can miss important details. It's like averaging out 100 pizza reviews and deciding that cheese pizza is the best by default. Boring. So how do we pick the perfect K? One of the best ways to scientifically determine the ideal K is cross-validation. Instead of just guessing, we test multiple values of K and check which one performs best on different parts of the dataset. It's like testing multiple pizza places before declaring which one is the best, instead of just trusting the first recommendation. Sometimes the best way to pick K isn't just through math, but by understanding the problem itself. In image recognition, larger K values can help smooth out noise and prevent misclassification. In medical diagnosis, smaller K values might be better to capture rare but important cases. While there's no one-size-fits-all answer, a common rule of thumb is to set K to an odd number, like 3, 5, or 7 to avoid ties, and to start with Kn, where n is the total number of data points. Then fine-tune from there. So now you know why picking the right K is the key to success with KNN. But hold on. What about different ways to measure distance? Can the wrong metric totally ruin your predictions? Oh, you bet it can. And that's exactly what we're tackling next. Imagine you're trying to figure out which city is closest to you. You could measure the straight line distance, follow the roads, or even count the number of steps it takes to get there. Each method gives a slightly different result. Right? Well, that's exactly what happens in KNN when we choose different distance metrics. And believe me, choosing the wrong one can completely wreck your model's accuracy. Let's break it down. KNN works by finding the nearest neighbors based on distance, but the way we measure that distance can make all the difference. It's like picking the right tool for the job. If you're painting a house, you wouldn't use a toothbrush, right? The most common distance metric is Euclidean distance, basically the shortest straight line path between 2 points. It's great when features are equally important and when the dataset isn't too high dimensional. But here's the problem. It's sensitive to outliers. Imagine you have one data point that's way off in the distance. It can pull the decision boundary in the wrong direction, just like one dramatic friend who always exaggerates and changes the entire mood of the conversation. Then there's Manhattan distance. Instead of measuring as the crow flies, this one takes the path along a grid, just like navigating a city where you can't cut through buildings. This works better in high-dimensional spaces and can be more robust to outliers. It's like planning your route in New York instead of teleporting in a straight line. But wait, there's more. Minkowski distance is like a shape-shifting metric. You can tweak it to behave like Euclidean or Manhattan depending on the situation. It's customizable, but also means you have another parameter to fine-tune. And here's where things get really interesting. Not all features are created equal. Imagine predicting house prices. Does it make sense to compare square footage and the number of bathrooms the same way? If one feature has much larger values than another, it dominates the distance calculations and makes KNN completely ignore the smaller scale features. That's why we normalize or standardize the data before applying distance metrics. So how do we pick the best one? It depends on the data set. If the data has a natural continuous space, Euclidean might work well. If the data is more like a structured grid, Manhattan could be a better choice. But if you're not sure, try both and compare. Picking the right distance metric is like choosing the right pair of shoes. You wouldn't wear flip-flops to a marathon, and you wouldn't use Euclidean distance for high-dimensional sparse data. Now that we've figured out how KNN decides what's near, let's talk about its strengths. Because while it might seem like a super simple algorithm, there are some serious advantages to using it, if you know when and how to apply it correctly. That's coming up next. KNN might seem like just a simple find your closest friends and go with the majority kind of algorithm, but don't let its simplicity fool you. It has some pretty powerful advantages that make it a go-to choice for many machine learning applications. So, why do people love KNN? Let's talk about its biggest strengths. First up, simplicity and intuitiveness. Unlike complex models that require pages of math and hours of training, KNN works on a straightforward principle. Store the data, compare distances, vote, done. There's no need to build a deep neural network or spend hours fine-tuning hyperparameters. If you can measure distance, you can use KNN. And here's the cool part. It doesn't make assumptions about the data distribution. Many machine learning models like linear regression or SVMs assume that data follows a certain pattern or shape. But KNN, it's totally flexible. Whether your data is spread out in weird clusters, shaped like a spiral, or even non-linearly separable, KNN can still work because it only relies on local relationships, not some predetermined equation. Then we've got effectiveness with small data sets. Because KNN doesn't train in the traditional sense, it shines when you have a limited amount of data and just need a quick, reliable way to classify something. Think about a doctor diagnosing a rare disease. There might not be enough cases to train a complex model, but a KNN-based system can compare a new patient's symptoms to just a handful of similar cases and give an accurate diagnosis. Another big plus, it can handle multi-class classification with ease. Some algorithms struggle when you have more than 2 categories, but with KNN, all you do is count which class appears the most, whether there are 2, 5, or even 10 different classes in your dataset. KNN doesn't break a sweat. And finally, KNN can be incredibly powerful when the right distance metric and value of k are chosen. We just talked about how important it is to tune these parameters, but once they're dialed in correctly, KNN can match or even outperform much more complex models, especially when the data is well structured. Sounds like a dream algorithm, right? But before you get too excited, hold on. KNN isn't perfect. In fact, it has some pretty big drawbacks that can make it completely impractical in certain situations. And that's exactly what we're talking about next.